Hello, everyone. It's my pleasure to welcome you to the next edition of QRST. And today we have some great speakers, and we'll start from Jerome Gonthier. Jerome is an application scientist at Zapata, and he has a lot of experience with quantum chemistry, quantum computing, variational quantum computing, and other things like this. And we will hear his presentation about resource estimation for NISQ devices. So Jerome, if you could share your screen.
Yes,
Great.
My pleasure.
And also, everything is recorded. It will be on YouTube, so no worries. Please, you can ask questions in the chat during the talk. That's not a problem. Okay, back to you, Jerome.
Thank you, Michał, and thank you for the invitation to speak at QRST. Today, I'm going to tell you a bit about uncovering challenges in the Variational Quantum Eigensolver through resource estimation, which is work we've published actually last year, I think. And it was a collaboration with people at BP. So quantum computing has the promise to help us simulate electronic structure systems because we can use a quantum system to simulate, electronic structure systems. And the promise is that, there is some considerable speedups that are possible in quantum computing compared to classical computing. So the goal is to reach quantum advantage in these electronic structure simulations, the point where quantum computer can solve a valuable problem better than the best known classical method. Now, because the current devices are noisy, the circuit depth is limited. So we have to combine quantum and classical resources in the variational quantum eigensolver. I think many people have heard about VQE before, but it's just a little review of the main components that are going to play a role in the resource estimation. The first one is the parametrized quantum circuit, which is what we call also an ansatz. So this circuit will prepare a trial wave function. And because it has parameters, we can modulate the wave function through these parameters. Then we need to measure the energy. So for that, we measure each operator in the Hamiltonian of the system. So molecular Hamiltonians have a sum of terms that can be pretty large. And we need to measure each of these terms to obtain the energy. And then we use the classical computer to average the measurements to obtain the expectation values for each operator. And then we compute the cost function. In the case of chemistry, it's going to be the total energy of the system. And we update the circuit parameters, in this case, to minimize the total energy of the system. So VQE is a heuristic algorithm. That means we don't have a mathematical proof that it's going to be faster than classical algorithms. We hope it can be faster because we know that we can represent an exponentially big wave function on the quantum computer efficiently. But we don't know if really it can provide a speed up over classical algorithms or an advantage over them. So to try to understand that better, we want to see what are the quantum resources necessary to obtain an advantage in VQE. And because it's heuristic, we don't have a mathematical proof. So we do that through benchmarking and resource estimation. In this talk, we're going to focus on the number of qubits, on the number of measurements necessary to do chemistry. And little spoiler, we uncovered a roadblock in VQE. A single energy computation for the ethanol molecule, which is pretty small, it has 3 heavy atoms, is estimated to take 71 days of sampling on 260 qubits. So we can get to 260 qubits, in reasonable future, but 71 days of sampling is pretty long, especially for a single energy evaluation. So now I'm going to show you how we get to this number. First, we have to choose a benchmark set when we do our benchmarking. So instead of looking at just one molecule, we want to look at a small set of molecules. So we see which results are robust to switching molecules. And we look at a specific quantity that we want to know in chemistry, which is the combustion energy. So most of the time in chemistry, the ground state energy is just a tool to get to a quantity of interest. So in this case, the combustion energy involves each of these molecules and then O2, and then the products of the combustion are water and CO2. The advantage of this test set is that we have accurate experimental data available, so we can readily check whether or not our results are close to experimental values. The disadvantage is that these systems are actually pretty easy to treat classically. So if we look at molecules that are said to be strongly correlated, which basically means they're difficult to treat classically, they may be better candidates for quantum advantage. So that's something to keep in mind, but we think our estimates are actually transferable to strongly correlated systems of the same size. What we look at in the benchmarking are a few different things. So the first thing to do is to look at classical computations, because we want to know what the state of the art for classical computations is, because that gives us what we want to beat with the quantum computer. So we need to know what can be the accuracy of the classical computations and about how long they take. Then we're going to look at the number of qubits, and we're going to try to reduce the number of qubits necessary for the system. It's not just a naive evaluation of this number of qubits. We're trying to apply some methods to reduce this resource and make things a bit more optimal. Then we look at the number of measurements we need, and we also use recent techniques to reduce the number of measurements. And finally, using all this information, we're going to extrapolate the runtime for the algorithm for VQE, given some assumptions on the underlying ansatz on device. So in total, all these experiments are about 1,000 numerical experiments, some of which were compute intensive, and we distributed, coordinated, and organized them through our platform Orchestra. I do a little bit of advertisement on the side. So now if we look at the classical benchmarks, I don't want to draw on everybody in quantum chemistry, so I'm going to try to explain all these abbreviations that quantum chemists really love. So we use this method called CCSD parentheses T. Basically, it's an approximate electronic structure method, and it's considered to be the gold standard in quantum chemistry. So usually, we would expect the results of this method to be very accurate, but it has an n to the 7 scaling, so it's pretty expensive. Then what we see on the plot here on the x-axis are different basis sets. So they also have a bunch of letters because it's quantum chemistry, but what these basis sets do is just discretize the problem so we can solve it on a computer. And the way to think about it is that the finer discretization means a bigger basis set and usually more accurate results. So here, when we go from the DZ of OXCC PV to the 5, it's double, triple, quadruple, 5. So it's just the size of the basis set. So here we see that when we look at the errors with respect to experiment, with a small basis set, with a coarse discretization of the problem, we have pretty large errors. And as we go to larger basis sets, we converge towards the experimental result, which is very encouraging. When we extrapolate the results, so it's like trying to get to the infinite basis set limit by taking results from the previous calculations, we see that we actually get a bit further away from experiment, and that is probably due to some of the approximations inside the gold standard method. So all of that shows that we can get to really good accuracy with classical methods, but it does take some effort. Even though these are small molecules, we need maybe about a day to do these computations and have the extrapolation work, the large basis set work. And then, maybe this indicates that for larger molecules, we could have some issues, because in larger molecules, this little error cancellation that we observe may not hold as well. And then larger molecules may also need these anharmonic vibrational contributions. So I don't want to get into details too much, but to be able to compare our results to experiment, we have to include the effect of vibrations. And doing that with harmonic approximations is pretty easy. And we can do that for the small molecules. But if we go to larger systems, it may not be as easy. And so it's essential to have a classical reference point to be able to benchmark quantum computing and understand when quantum advantage could appear. So then we looked at how many qubits we need. So for that, we also use classical computations because each element in the basis sets I was speaking about before can be mapped to 1 qubit. So the larger basis set you need, the larger discretization of the problem you need, the larger the number of qubits. So what we did is we compared these electronic structure energies with the full basis on those, and we compare that with energies with truncated basis. So it's a way to prune points in the grid, if you want, and reduce the number of elements necessary. So there's this FNO method to do that. That's known in quantum chemistry. It's just a way to prune this grid in a smart way to retain only the most important information. And then the truncation error is actually corrected using perturbation theory just to get us as close as possible to the original result. So the goal of this estimation is to have some scalable measure of how many qubits we need. We don't want to just have a number for each molecule. We also want to understand, how many qubits we would need for larger molecules. So for that, we looked at the number of qubits needed per active electrons. So it's just the total number of qubits divided by the total number of electrons in the computation to try to have a scalable measure of that. And so we look at these truncated energies on this plot here, where at the bottom we have the truncation threshold, basically. The smaller the threshold is, the closer we are to the full basis limit. And then we just explored different truncation thresholds, and we looked at when we would get close enough to the original result. So here, close enough means chemical accuracy, which is defined as 1.6 millihartry. The reason it's defined like that is that it's similar to the accuracy you can get in experimental results. And because the goal of the simulation is to be able to accurately reproduce the experiment. And so if we are within experimental error bounds, that's enough. So what we saw exploring these different truncations is that we needed about 13 qubits per active electron to be able to be accurate enough. So for example, if we have 10 electrons in the molecule we are looking at, that means we would need 130 qubits to be able to get the energy to enough accuracy. After that, we look at the number of measurements, which is the less chemistry-oriented part of this talk. So in looking at the number of measurements, we first need to transform the fermionic Hamiltonian of the molecule to qubit Hamiltonian. So that means we simply get the Hamiltonian as a sum of Pauli strings associated with coefficients, hi. And then the ground state energy is the expectation value of this Hamiltonian, which is written as the sum of the expectation values of the Pauli strings with the coefficients. So that means we need to measure each of these Pauli strings with enough samples so that we get the expectation value with enough accuracy for each operator. So how many samples is enough samples? We can actually do a statistical analysis and understand that. So one thing we can also do is group the different terms in the Pauli strings so that we can measure some of them together. And that allows us to reduce the number of measurements in some cases. So it's simply rewriting the Hamiltonian as a sum over the groups and then a sum over each member of the group. And when we do that, we know we can write the number of measurements needed to reach a given accuracy epsilon as k over epsilon squared, where k is just a constant that depends on the molecule and a number of other factors. And then epsilon is our target error. And k can be expressed as this sum here that contains the coefficients of the Pauli strings and then the covariance between Pauli strings in the same group. So Pauli strings in the same group are measured at the same time, and that's why we need to include their covariance here. This expression actually optimally distributes the number of measurements among different groups. So we don't need to worry about that. In that case, we can obtain this expression by just writing down the optimization problem, and it has an analytical solution, as was shown by Nick Robin in this paper. So that's what we can use to estimate the number of measurements. Then the question is, how do we estimate K? So K depends on the covariances between Pauli strings P alpha and P beta. So in the case where alpha is different from beta, so that's a real covariance, we actually assume them to be 0. So covariances can be positive or negative. So what we did here is assume that we have a random distribution of covariances. And so overall, they kind of cancel out. When alpha equals beta, then it's the variance. So for the variance, we did 2 different estimations. The first is just take the upper bound of the variance, which is 1. Or we can also use this classical electronic structure method, CISD, quantum chemists-like abbreviations, like I said. So basically, this method allows us to compute the variance with an approximate classical wave function. And we use this method because it's just pretty convenient to extract the needed information from the existing software packages. Then K also depends on the coefficients, H alpha and H beta. So to get these coefficients, we do a Jordan-Wigner transformation of the fermionic Hamiltonian, and we use 2 different representations, this FNO method that allows us to do smart truncation, and then the canonical orbitals that are just coming out of the Hartree-Fock calculation. So that's what most people use when they do chemistry with VQE. They get the orbital from Hartree-Fock. And then we can do different grouping methods for the terms in the Hamiltonian. The simple qubit-wise commuting grouping means that if we have Pauli string X1 and Pauli string Z2, we know we can measure them together. We don't need to add additional entangling circuits at the end of our quantum circuit to measure things together. We just measure things together when they are simply compatible this way. And the way we built groups was using this sorted insertion method, which sorts the Pauli strings by highest coefficient first, and then just tries to put them into groups as big as possible. And then the other grouping method we used was this basis rotation grouping. So in this method, we actually add a circuit at the end of the quantum circuit to rotate the basis. And then that allows us to measure a lot of the Pauli strings together. So the difference between the 2 grouping methods is whether or not we have to add additional operations at the end of the circuit. And then we estimated the value of K for all our molecules using Hamiltonians that had up to 80 qubits. So the way to do that was just to take the full Hamiltonian in the basis set we chose, and then we truncate at different number of qubits using either this FNO method or the canonical orbitals. So the reason why we did that is so that we have a bunch of different points at which we can compute K, because we cannot handle things that are much larger than 80 qubits with the current code. It's a bit difficult. So when we have all of these points, we can simply fit a line through these points and extrapolate to larger molecules. And so that's what we did here. We see the results for all molecules. That's why we have different points at the same number of qubits. These are different molecules. And then we fit this expression that's A times number of qubits to the power B, where A and B are our fitting coefficients. And here we show the scaling that we obtained for all of these methods. So that shows the scaling of the number of measurements, basically, with the number of qubits across different molecules. So the first thing we notice is that using this simple grouping strategy, that's the qubit-wise commuting, we have a scaling that's close to n to the 5 to n to the 6, which is reasonably close to what is expected theoretically. And then when we switch to this basis rotation grouping, now the circuits are a bit deeper, so we're going to accumulate a bit more noise, but the measurements only scale as n 2.3 to n 3.6, so close to n squared to n cubed, which is much better. We see a number of other things like this FNO method that is doing smart truncation, actually requires more measurements for the same number of qubits. But on the other hand, we get more accurate energies for the same number of qubits. So here we get more accurate energies, but we have to pay for it a little bit in terms of the number of measurements. And finally, this data allows us to extrapolate runtimes for each molecule separately. And in that case, we do the fit for each molecule separately. There's one more thing we can do to reduce the number of measurements, and that's using this reduced density matrix constraints method. So this method that was published by Nick Rubin as well takes advantage of known relationships between elements of the one particle and the two particle fermionic RDMs. And so because we know these relationships, we can write them as an expression that's equal to 0. And then we can add these expressions to the Hamiltonian. And so they're not going to change the Hamiltonian because they're not going to change the spectrum of the Hamiltonian because their sum is 0, but they can change the variance of the Hamiltonian. So we can optimize the coefficients beta here, the weight of these different expressions, to minimize the variance of the Hamiltonian and try to require a little less measurements. So because we couldn't use this method for up to 80 qubits, with the current code, because it's a prototype code, we only explored for a small number of molecules. And we looked at what was the reduction factor in terms of the number of measurements that we observed. So the reduction factor can vary, and it seems to be also sometimes decreasing as a function of the number of qubits. So we assume that this allowed us a reduction factor of about 2. So that gets us to the runtime extrapolation itself. So we built a runtime model from the previous data. Here we assume 2 qubit gate times of 100 nanoseconds that are on par with superconducting architectures, multiplied by the number of measurements, multiplied by the depth of the ansatz. Here we assume the depth of the ansatz is growing linearly with the number of qubits. That's an optimistic assumption. And then we also took into account this basis rotation grouping that adds a circuit. And that's how we get to this 5n qubit minus 3. Number of qubits is estimated to be 13 times the number of electrons. And then the number of measurements is estimated from extrapolating k using what we think is the best method. So we approximate the variances. We use this good truncation method on the basis rotation grouping. And then we added a factor of 2 here to take into account the RDMC effect. Finally, we set epsilon to half a millihartree because we allow some error for the truncation of the basis and some error for the device noise. So this runtime extrapolation neglects single qubit gate times, measurement times, qubit reset times, etc. So we think it's actually an optimistic runtime extrapolation. In spite of that, we see that we actually need several billion measurements for these small molecules, even with the measurement reduction techniques. And so that gives us runtimes that go from 2 to 71 days on an idealized device where we didn't even take into account the effect of noise on the number of measurements. And all of that is for a single energy evaluation. So when we do VQE, we're going to need to do a lot of energy evaluation to actually optimize the quantum circuit. So in summary, it's necessary to first evaluate the performance of classical methods to understand how they're doing. And in that case, we can reach chemical accuracy for combustion, but it's not completely trivial. So for larger molecules, we may have some difficulties and need some higher level methods that may be complicated to use. We saw that using this FNO method, we can reduce the number of qubits efficiently, and that the basis rotation grouping is good at lowering the measurement count on the scaling of the number of measurement. But in spite of all of that, chemically accurate VQE for the combustion of these small molecules still seems to require years of sampling if we want to have enough energy evaluations to optimize the parameterized circuit. So the way forward is possibly to parallelize measurements across lots of devices. to look at other measurement and qubit reduction techniques that have been published since our work. There's been a lot of new ideas in this field that are worth exploring, but they will need to yield order of magnitude improvement to help us. And then there's estimation methods that go beyond operator averaging, some of which published by Zapata, like enhanced likelihood function or Chebyshev likelihood functions that we grouped under the robust amplitude estimation term. Finally, another possibility is to look at effective Hamiltonians, where we try to simplify the problem, treat as much of it as possible on the classical computer, and only keep the very hard part on the quantum computer. So I would like to acknowledge people from Zapata and from BP for help on this work. Jonathan, Max, Alex, who are co-authors, Chris, who helped us with the project, Maria, who helped us with the slide, and people from BP for their help on the project and their support. And if you want to hear more about this work and maybe about the next steps we took after this work, I'm giving a talk at this quantum chemistry conference, July 3rd to 8th. So if you like quantum chemistry, think about it. If not, you're probably gonna get a little bit bored. And I'll be happy to take any questions.
Thank you very much, Jerome. Do we have any questions? If so, please raise your Zoom hand and unmute yourself. Okay, Alireza?
Yeah, do you hear me?
Yes.
Okay, thanks for your talk. I wanted to ask about that estimation about the wave function ansatz. That linear assumptions. You also mentioned that there is optimistic. What is the realistic assumption you think, and how that can help to improve the results?
Yeah, that's a good question. Here, I think, it's still an open question in research. What is exactly the depth of the ansatz you need to represent a problem accurately? And it might depend on the molecule. But we try to be a bit optimistic to have something that would work with the runtime estimation. So the idea here is that we consider to have like a layered ansatz that uses like these 2-qubit gates that are in some kind of brick pattern that allow us to entangle everything together. And we assume that if you take 2 times the number of qubits as the number of your layers, and each layer is actually a depth 2, then you can get enough entanglement to get an accurate result with your wave function. But we haven't, it's a lot of speculation here. We haven't really explored that.
So you see more chance for the device-friendly ansatz rather than physically motivated quantum chemistry ansatz?
Yeah, because if you look at the UCCSD ansatz, for example, it's much, much deeper than that. And with the current noise levels on the device, that's very difficult to get anything really useful after that.
Yeah.
So maybe things like adapt VQE, that use like an adaptive construction of the ansatz from a pool of operator are good things to look at. There's also a paper by Rob Parrish where they designed this gate that's meant to conserve particle number on spin for molecules. So that's very useful because then you only explore the part of the Hilbert space you're interested in. So there's a number of like interesting work that has been published, looking at good ways to build ansatzes.
And then one short question, what about the classical overhead? Do you see it as a problem that arises?
Yeah, so the classical overhead is a good question, and that's the reason why we couldn't really go beyond 80 qubits. But I think the main reason is also because we're not using efficient data representations. When we represent a qubit Hamiltonian, like in open fermion, it's this big data structure that stores like a lot of the operators and coefficients. I think there's ways we could store that much more efficiently. It's a problem that people have had in quantum chemistry because the 2 electron integrals also scale as n to the 4th. So they become very large when you have basis sets that are very large. But we have come up with solutions that allow us to do calculations with basis sets of like thousands of, that corresponds to like thousands of qubits without too much problem. So I think it's a lot of like software engineering on transferring these solutions there for like getting the pre-processing. For the RDMC method, maybe there's more effort to do to like optimize the code, because I think it's less known how to do that really efficiently. But for like handling Hamiltonians and stuff like that, I think, you know, we know how to do it efficiently, but we haven't really implemented it yet.
Thank you.
Great. I don't think we have time for more questions, so sorry for that. You can type them in chat. So thank you very much, Jerome.